Normal distribution is really useful, models many physical situations, and it's described using its mean and its variance. I'll just turn this around so I'm not in so much shadow. Okay, it's described using its mean and its variance. And we tend to do everything on the calculator. You need to know these facts. Virtually all data lies 3 standard deviations either side of the mean, saying 99.7%. That's virtually all data lies within 3 standard deviations of the mean. Approximately 95% of the data lies 2 standard deviations away from the mean, and approximately 2/3 of the data lies 1 standard deviation either side of the mean. So you need to know those 3 facts. We have the standardized normal variable, which we find really useful. Standardized normal variable has a mean of 0 and a standard deviation of 1, and that's how we find the standardized normal variable. And we also know that if we have a large value of n, and if n times p, this is from a binomial. If we have a binomial where we have a large value of n, if n times p is greater than 5, and n times q is greater than 5, now that's where q is the probability of a failure, then you can approximate that binomial distribution using a normal distribution, where the mean is n times p, and the variance is n times p times q, where q is a failure, or n times p times 1 minus p. On your exam questions, what they're really saying is the condition to have a good approximation, normal approximation to the binomial is you need a large value of n. There's also, very briefly, it talks about points of inflection of the normal distribution curve. Now, it's difficult to see how they would ask this, but it's good that you know it. It is on your syllabus. So if you look at your normal distribution curve here, you can see it's all these curves are always symmetrical about the mean. So you can see that the mean is 12. There's a point of inflection at 8, and there's a point of inflection at 16. So you've done quite a lot about points of inflections in the pure part of your A level. And what the normal distribution says, that the points of inflection of the normal distribution curve lie 1 standard deviation away from the mean. So we're going to now use this curve to estimate the standard deviation. So if the mean is 12 and the points of inflection are at 8 and 16, you know 12 plus the standard deviation is 16, 12 minus it is 8. So that means your standard deviation is 4. You know, if you couldn't see it, you'd be able to solve them simultaneously, but obviously you can clearly see that one. So here you've got x normally distributed with mean 12 and variance 4 squared or 16. Right, examples. So our first example is straightforward normal probability that you would use your calculator for. So if x is normally distributed with mean 20 and variance 9, you can see if you do a little sketch, it's easy to visualize. So the probability of x being less than 17. Now the normal distribution is continuous distribution. So x is less than 17 is the same as x is less than or equal to 17. Very different to the binomial. It's continuous. You can't actually find the probability of a precise value. It's all about regions. So I can visualize here from my diagram that I know the probability will be less than 1/2. So I just put that into my calculator. Just check with your teacher if you're not sure how to do that. And I've got 0.159. If I was given a normal distribution like I am here, where the mean is 12 and the variance is 3, and I was told the probability of x being greater than the value is 0.7, and I needed to find a, I would use the inverse normal. If I visualize that, again, symmetry about the mean, I know that a is going to be less than 12. So if I enter that into my calculator using my inverse normal, I want the right tail and the area to be 0.7. So I'm getting 11.09, and that makes sense with my diagram. Right, third example. If I don't know a mean or a standard deviation, if I don't know either of them, I'll need to use simultaneous equations. But here I only have one unknown. Whenever you have any unknowns, you are going to use your standard normal distribution, Z. So I've also been told that the probability of x being less than 30 is 0.2. So 30 is my x value here. So visualize what's happening. I don't know mu, so I'm using my standard normal distribution. So here's my standard normal distribution with mean 0, and I'm going to find the value of Z. I use my inverse normal, and when I put that into my inverse normal, obviously I've got a left tail, area 0.2, standard deviation 1, mean 0. So my Z value is minus 0.842. I know that that's how I calculate my standard normal value of Z. So substitute your values in, rearrange, and I've got mu is 32.06. Right, last question. A fair coin is tossed 100 times. Now that's quite a lot of repetitions. What's the probability that there's more than 60 heads using the binomial? So if you set up your model, greater than 60, binomial has to be discrete, so that's greater than or equal to 61, which is the same as 1 less. The probability of x is less than or equal to 60. Put that in your calculator, 1 minus BCD, 60, 100, 0.5, and I've got 0.0176. Part 2, you're going to do exactly the same question using the normal approximation. Right, you know that the mean is n times p, which is 50, and the variance is n times p times q, or n times p times 1 minus p, which is going to be 25. So you've got normal distribution where the mean is 50 and the variance is 25. The probability of being greater than 60. So if you visualize what that's going to look like, you can see that that's going to be less than a half. So greater than 60, your lower is, so it's straightforward normal and cumulative normal. So lower, you've got 60, upper, it's huge, your variance, your standard deviation is 5, your mean is 50, so your probability of x is greater than 60 is 0.0228. Not a great approximation.